Hello everyone. This is the first video for Unit 3, the linear functions unit. So this video will describe these three pre-class assignments and will cover the functions basics and the intercepts video. This is the first part of the unit after Unit 2 is due. So this stuff is due 7/3 by midnight, and your Unit 3 exam is 7/6 by midnight. Notice that your Unit 2 linear equations exam is due this Sunday, and your homework for Unit 2 is due by this Friday. Okay, so these three assignments are due 7/3, which is a Thursday night at midnight. Okay. This section basically takes your linear equations and casts them as a thing called a function. All linear equations are functions, so this is an easy transition. First of all, a relation is just some arbitrary set of points. In your previous unit, you were asked to tell me if a given set of xy's, right, a certain set of points was linear, and you would check the slope. If it had the same slope for all the points, it was linear. The ones that didn't qualify as linear, that didn't have an equal slope, would be relations, right? Wouldn't be slopes aren't equal between points. So it's just some arbitrary set of points. Now a function is very specific. A function is a very specific type of relation that has one specific requirement. Basically, let's look at the English of a function. What a function is for each and every input, there can only be one output. Now that's basically what all these words state. Now I want you to pause the video and read this paragraph. I'm not going to read it for you. But all of these are linear equations. So anything that is a linear equation, it's linear because h isn't to a power, right? F isn't squared, h isn't squared or cubed. It's just to the first power. All of these formulas are functions. Rewrite them using function notation. So to write c in terms of function notation, basically instead of calling this c, we're going to call it c of f. Notice up here, x and f of x. F of x is the function notation for y. So we could rewrite all these. C of f equals 5/9 f minus 32. W of h equals, right, wage in terms of h. So wage depends on hours here. Celsius depends on Fahrenheit. H minus 40 and f of h. Femur depends on height equals 0.432 h. This is a 2 right here. Minus 10.44. So I've rewritten all these in function notation. Now you're probably saying, well, can I just solve this equation for h by adding 10.44 and then dividing by 0.432 and say h of f equals something, times f? Yes, we'll get to that at the end of this unit. That is what's called an inverse. But right now, the way this equation is written, h is the independent variable and femur is the dependent variable. So height is the independent, femur is the dependent. Here, hours is the independent, wage is the dependent. Here, Fahrenheit is the independent variable, and Celsius is the dependent variable. Now, how do I test for this to be a function? Do I have to map a whole bunch of points and do some type of exhaustive approach? No. We have something called the vertical line test. Now, for something to be a function, that means for each input, you can only have one output. So if I plug in 3, it can only send me to one place. Notice here, if I plug in 0, it sends me to two different places on this graph. It sends me here and here. So therefore, this fails the vertical line test. Because as I do vertical lines, notice how it touches it more than once. So this one fails and this one fails. Because as I draw a vertical line, it touches more than once. Think about it, it's like putting into a Pepsi machine and pressing the Sprite button. So your input was the Sprite button. Now the Sprite button can't send you back a Pepsi and a Sprite, it can only send you back a Sprite. So this is a function, so for any input, you're getting one and only one output. When I press the Sprite button, I have to get back a Sprite. I can't get multiple outputs for it. So A and C both pass the vertical line test. And basically how the vertical line test works, I just explained. If it touches your graph once and only once, it passes. Notice here and here, it only touches once. These two cases, it touches more than once. Here twice, here it touches 1, 2, 3, 4 times. Okay. Now, generally, now we're going to talk about domain and range. This is a concept that is difficult for some people to grasp. So now, what I'm going to do is erase this stuff off these graphs so I can really talk about domain and range without it getting mixed up with this other notation. All right. So, graph A, let's talk about the domain and range. The domain is always the inputs, or the x's, right? The x-axis. And range is always the outputs, or the y-axis. I want to go back and call it axis. X-axis and y-axis. Okay, so now, just looking at the x-axis, that's all we care about. I'm going to take my highlighter and put what values of x are being graphed by this thing. So if I went all the way out here to x is 1,000,000, would this graph eventually get there? Yes, because this arrow's pointing up. So our domain for this graph is everything along that line. So therefore, our domain of function A is negative infinity to infinity. Kind of erase this so I can make it a little bit smaller. Okay, now let's look at the range, the outputs. So I'm going to use a different color here. So this one, our domains are going to be in yellow, and for this one, our ranges are going to be in green. So our range, notice there is no range down here for any y values down here in the negatives, right? Negative 1,000,000. There's nothing in the graph. The graph does not start until right here at this y value, which looks like it's in between -3 and -4. So our y values start getting mapped right here and go all the way up out to infinity. So therefore, going from small to big, nothing, 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 my first point is negative, we'll call it 3.5, and it does include that point. So we're going to use our bracket notation. Let me make that a little bit smaller. Okay, so we're going to call this bracket negative 3.5, and the graph extends out to infinity. So whenever you use infinity, always use a parenthesis for infinity. Okay, next graph. Using our yellow, let's go in here, our x values, nothing, 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 doesn't start till here, and then it maps to here, and then it stops. Looking at this graph C, it goes all the way from here, all the way across. These arrows extend out forever. Looking at graph D, it looks like this arrow extends this way forever on the x-axis. And this arrow is even turning back and looks like it extends this way forever. So this graph even is all. So now let's go in and make our domain. So our domain for B is from this number, so that's -1, -2, -3, -4, -5 to 1, 2, 3, 4, 5. -5 to 5. And you always put brackets if it includes the point. Both of these graphs go across all real numbers, so I could write negative infinity to infinity or all reals. Either those two things are synonymous. All reals and negative infinity to positive infinity mean the same thing. These two things mean the same thing. They are equal statements. Okay, now let's go back and look at our range. So now looking at our range for the circle, looks like it starts here and goes to there and then stops. Looking at our range for the line, it looks like this thing goes off forever in this direction and this arrow goes off forever in that direction. So our range goes forever. Same with this graph. It looks like it goes all the way off to negative infinity, and this thing seems to point off where it's gaining ground all the way up to positive infinity. You know, this graph is not a function, and it's really difficult to know exactly, but by the information that we're given here, it seems that our domain and range go off forever in both directions. So here, our range is from 1, 2, 3, 4, we'll call it negative 5 to 5 again. And here, our range is all real numbers, and the same with this one, all real numbers. Or negative infinity to positive infinity. These two statements mean the same thing. Okay? Now I want you to take a look at graph C. Graph C is a line. This is a linear function. All lines, when you don't have an application attached to it, when it's just simply the function itself, the domain and the range are always all real numbers. They're always negative infinity to infinity. Notice I have parentheses anywhere I have infinity symbols, and I have brackets anywhere I have a number because the graph touches that number. And I think it's really useful to color in the axes wherever the graph appears so you can look at it kind of at a one-dimensional basis. So looking at this just on the x-axis, it goes across the entire domain. Looking at this just on the y-axis, it goes across the entire range. Okay. Now, let's go a little bit deeper. Looking at graph A, how do we determine which ordered pairs would satisfy the functions that created it? Well, let's take this point for example right here. It seems the graph seems to go through 0, 0. So whatever function created it, when I plug in 0 for x, I better get back 0 for y. Or even zooming in, it almost looks like 0, 1. It's hard to tell exactly from the graph. Again, looking at graph A, does 1, negative 4 lie on the graph? So let's look at 1, 1, 2, 3, 4. Here's 1, negative 4. That answer is definitely no. What does that mean? It doesn't satisfy the equation. Means it doesn't make it true. Name 3 ordered pairs that lie on the graph and 3 that do not. Now it's hard to tell exactly what lies on the graph, so let's just answer the next question. Since we don't have functions attached to these and we won't know for sure, we're just kind of guessing. What generalizations can you make about the ordered pairs that lie on the graph? All the ordered pairs that lie on the graph satisfy the function or equation. Let's say equation. The ones that do not lie on the graph do not satisfy. So they do not make it true when you plug the ordered pair in to the equation. Okay. Let's look at this. Okay. In the examples below, the notation is different, but the concept is the same. So for the next few functions, we're simply using our input-output method to graph. So we're just taking inputs, what do they give us back as an output, put them on the Cartesian coordinate system, and connect them with the line. Okay. Find ordered pairs that lie on the function's graph. However, this time we are only given one coordinate. Which coordinate are we given, the x or the f of x? You may wish to organize the information using an f of x table. We're going to do this a lot. We've already done it in Unit 2 when we created our linear models. This makes it easy to see the relationship between the two. When finding ordered pairs for a function, keep in mind the sentence, when x is blank, f of x is blank. So here we're going to call this x and g of x, so this is our x function, or x axis, and this is our g of x axis. So now when the x value is 2, this is when x is 2, notice the g of x value is 0. Another way to write it is this is equal to g of 2. When x is 2, g of x, g of 2 is equal to 0. Let's say when x is negative 2, what is g of negative 2? Let's go over here where x is negative 2, 1, 2, negative 2, so then count up 1, 2, 3, 4. So x, when x is negative 2, g of x is positive 4, so g of negative 2 is equal to 4. If I could do this infinitely, there are an infinite amount of points that satisfy this equation. Do it again. We could say when x is 0, we could say g of 0 equals, when x is 0, g of x is 2. And I could do this forever. These two things are the same thing. They carry the same information. They're just casted a little bit different. Once again, let's find these three things. So let's find f of negative 5. So when x is negative 5, f of negative 5, I'm going to put that parenthesis in right here, equals 1, 2, 3, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. When when x is negative 5, f of x is positive 5. Now let's try negative 3 and 1. So f of negative 3, f of 1. Let's count back. 1, 2, 3. So we count down. 1, 2, 3. So this is negative 3. So when x is negative 3, f of x is negative 3. And then let's try 1, 1, 2, 3, 4, 5. So which equation is the correct for this function? So which equation do all three of these points satisfy? So when I plug in negative 5, negative 3, and 1, they give me back 5, negative 3, and 5. So let's try the first one. F of negative 5. Now I need it to equal 5, right? So this over here, I'm going to write in equals 5. Let's see what it equals. Negative 5 squared plus 4 times negative 5. Which equals, negative 5 squared is positive 25, 4 times negative 5 is negative 20, and indeed it does equal 5, so it does satisfy. Next point, f of negative 3 equals, so negative 3 squared is positive 9, minus 12 is negative 3, so it does check out. Let's try f of 1 equals, 1 squared is 1 plus 4 times 1, so 1 plus 4 indeed is 5. So it does satisfy that equation. Let's try the other ones just to make sure. Here, when x is 1, f of 1 does not equal 5, so it can't be that one. And here, f of 1 does not equal 5 either. It equals 29. So it can't be that one either. So this is the function, the equation that is correct for this function. Now we're not going to deal with solving anything with this function yet, with this quadratic. That'll be for the next unit. This is simply taking ordered pairs. Can you plug in an x value, evaluate, get a y value, and plot it on a graph? Okay. When given the equation for a function instead of its graph, the ordered pairs have to be determined algebraically. So let's look at an example. So let's plug in these x values for f of x and then graph it. So when x is negative 3, f of negative 3 equals 3 times negative 3 squared minus negative 3 plus 2. So what does this equal? It equals negative 3 squared is 9 times 3 is 27 plus 3 plus 2. So this is 32. And keep going. So negative 2 squared is positive 4. Positive 4 times 3 is 12. Plus 2 is 14, 16. 0 is going to be 2 because these two things go away. Negative 1 squared, f of negative 1 equals, negative 1 squared makes it positive, so it's 3 plus 1 is 4 plus 2 is 6. When I plug in 1, you get 3 minus 1 is 2, so that's 4. Here we plug it in, 4 times 3 is 12, minus 2 is 10, plus 2 is 12. When I plug in 3, f of 3 equals 3 times 3 squared minus 3 plus 2. So that's 3 squared is 9 times 3 is 27, minus 3 is 24, plus 2 is 26. Now notice that 3 and negative 3 do not give me back the same value. This is not, they're not mirror images of each other. Negative 3 and 3 do not have to give you back the same value. So let's plot this. Now these numbers are really big, 32. So I'm going to have to plot 32 on this y-axis somewhere. So what I'm going to do is make each line per 5. So each line is 5 units on the f of x axis. Not on the x axis though. So 0, 2, so that's going to be about right here. Negative 1, 6, so negative 1, 5, here's negative 1, 6. And then 1, 4 is going to be about right here. 2, 12, 5, 10, there's about 2, 12. And then negative 2, 16, so 5, 10, 15, there's 16. Three is 26, so 1, 2, 3, 5, 10, 15, 20, 20. And negative 3 is 32, so 5, 10, 15, 20, 25, 30. Now, what I want you to notice is these points are kind of off. You know, they're not symmetric in the sense that this point's not here, so the bottom of this parabola is not at this point. The points picked on this graph have nothing to do with where the bottom of this thing is, where the bottom of the parabola is. These are just arbitrary x values that were picked for you. We'll find another method in the future for finding where this thing bottoms out. And we have a specific name for that called the vertex. So right now, you don't know exactly how to identify where this thing bottoms out, but it's going to be somewhere in between 0 and 1. All right? Or maybe even 1 and 2. We don't know for sure, but we can still come up with some vague description of what the graph looks like. Okay. Determine if the given ordered pairs for a particular function. So, which, if any, of the following ordered pairs work for the function? So when I plug in negative 2, negative 2 squared is 4, so that one works. That one works. Negative 1, so square that. Negative 1 is negative 1 squared becomes positive. So that's actually 2, so that one doesn't work. 5 squared is 25, that one doesn't work. 4 squared is 16, so that one does work. So these 2 points do work. So now let's look at these 2 graphs. These 3 graphs. Do either of these 3 graphs contain these 2 points? So negative 2, 5, this graph does not go through negative 2, 5, so it can't be that graph. What about this one? Here's negative 2, 5. This graph does go through negative 2, 5. What about this one? Negative 2, 5. It could. I'm not sure. Let's check the other point. 417. So this one goes out to 4 and up to 17. It could be this one. Let's go out here, 4 to 17. It could be this one. So we're not exactly sure about these two graphs. Let's test another point, because we're not narrowed down yet. Let's try 0, because notice when this graph, well, let's not try 0, because when this graph, when x is 0, y is 1, the same thing with this graph. Let's try a point where they differ. Notice when x is 1, this one's equal to 2. This one, when x is 1, it's equal to 0. So let's plug in 1. So let's find f of 1 from this graph, or from this function. So f of 1 is going to be 1 squared plus 1. That's 1 plus 1, which is 2. So when x is 1, this one goes through 0. It can't be this graph. It has to be this graph. So this function, f of x, x squared plus 1, goes to this graph. Same thing. Let's look at another one. Negative 2 comma 4. When I plug in negative 2, that gives me 1. Negative 1. Negative 1 plus 3 is not 4. It can't be that point. When I plug in 4, 1 half of 4 is 2. 2 plus 3 is 5. That point does satisfy. What about 6? 1 half of 6 is 3. 3 plus 3 is 6. What about when I plug in negative 4? Negative 4 divided in half is negative 2. Negative 2 plus 3 is positive 1. So all three of those points satisfy the equation. Now let's do negative 4 comma 1. Does this graph go through negative 4, 1? No, it's already past it. It can't be that graph. What about this one? When x is negative 4, does it go through 1? No, it can't be that graph. This, when x is negative 4, it does look like that one satisfies. 4, 5 is definitely satisfied, and also looks like 6, 6 will be satisfied. So it is that graph. This is the graph. This function is linear. Notice how x isn't to the first power, so therefore the graph, or is to the first power, so therefore the graph is a line. This x isn't squared like in the previous example. That produces a graph that looks like this. So your functions basics assignment is due 7/3 at midnight. Now there's not any paper homework to turn in with this assignment, but with the intercepts assignment there is. So let's move on a little bit more. Let's look at an actual application. Actually, what I'm going to do, class, is I'm going to do the next video, the applications will tie in to the next assignments. So I'm going to stop this video right there at your functions basics. You have a homework assignment to go try. It has about 9 questions, I believe. Let's kind of pull it open. Yeah, it has 9 questions for you to answer. So now you have all the ammo you need to answer these questions. Got some interval notation, stuff like that. I have the viewing examples in there. Also, another helpful video that could help you with the function stuff is here at Khan Academy. What is a function? He really goes through what's the difference between equations and functions. So he really relations and functions. So it goes over a lot of the same stuff that I covered in this video. All right, class? I'll look forward to my next video tomorrow. Thank you and have a wonderful day.